So when I go and I look at the schedule that we had or that I had kind of penciled in before we left for break, I have the test scheduled for Friday. Yeah, I know. I feel kind of the same way about that. I don't know if that's I don't know if that's totally realistic. So let's just kind of. I'm thinking I might do like an extra section and push that test into next week if that sounds better to you guys. Yeah, so we'll plan on doing that. And I think I would like to do that extra section today while I'm still thinking about it. So I'll be rearranging the schedule here for the week. But before I start on any of that, do you guys have questions on these volumes problems that we've been really kind of focused on for about a week now? It's been like 3 class periods or something. We've basically just been doing these volumes of rotation kind of problems. I think on the snow day last Thursday, I'd left you with like 3 FRQs to work on. I think 2 of them were volume of rotation, and 1 is like review of like first semester kind of topic. But I figured I'd start with that. I think that's the most difficult thing that'll be on this this next test. Elena. Let's see. Okay, so let R be the region between these 2 curves from 0 to 1. So I'm going to start by just kind of sketching a picture of that. And again, to do that, I'm going to employ my calculator. And I'm going to set my window from, I'll do like 0 to, I guess 2. And then maybe -2 to 2 or something. Oops. Those are the wrong spots. -2 to 2. Just to get a picture. Now, I swear I hit negative there. Okay. Oh, one moment. We're in degree mode. Ah! All right. Okay. So we have this is like my region R would be like this area in there, right? So I'm just going to kind of sketch that onto my sheet of paper so that I can draw that. So for A, that's going to be the integral from 0 to 1 of the upper function minus the under function. That's it. Okay. Are we good with the integration? Do you need to see that, or can we just do setups here, Elena? You're good with just setups? Okay. I mean, I'm happy to grind through this. It's just like more time, So then it says set up, but do not integrate the integral expression in terms of a single variable for the volume of the solid when it's rotated about the x-axis. So if we're going this way, we're going to have like kind of like a heart shape, but it'll be really deep. It'll be kind of what that looks like. So that certainly's got a concavity to it. So I'm going to try to do this by using washers. So like my inner radius would be that, and my outer radius would be going to that function. So again, we're going to be integrating from 0 to 1. So my outer function squared, minus my inner function squared dx, pi. Okay with that? And then for part C, it says, what if we're rotating about the y-axis? So here, we're going to have a concavity, right? Like when we do this, we're going to have a similar three-dimensional shape that's kind of heart-shaped-ish, but with a gap in the middle. The problem is that, like at least for part of it, like my R inner and my R outer are the same. So you could do this two different ways. You could break this into two three-dimensional chunks and do like a shell for the top half, and then just like an easy disk method for the bottom half. Totally doable to do that. Or I think, we can do this with one single integral too. I did this before and I thought I came up with something kind of clever that worked. But now after a week of sitting on my buns not doing much, I can't remember at all what my tricky little plan would have been. So I need to double check at what I came up with here. All right. So if we do this, I guess So again, we can do this in like one of two ways. So if I want to do this with shells, I can go the whole thing. Where my radius is going to just be like some x value, and then the height is going to be like that guy. So my radius is going from 0 to 1 because that's as long as that radius can be, and we'll have x times, and then that height there is going to be the 1 plus sine pi x minus x squared dx. Or we could break it into two pieces by using like a disc and a washer. So in doing that, we're going to like chunk it there. So this section is the disc, and then I can do this upper section as a washer. I just have to be a little sneaky about it. So my disc would be the integral from 0 to 1, and then this is like my radius. So I have y equals x squared. So I have x equals then plus or minus the square root of y, right? So that's the first one, and notice that, you know, the squared blows up the plus or minus, and it also cancels out the square root, so that just turns into a y there, which is pretty nice. And then from 1 to 2, we're going to be doing this washer. So my R inner is like this, and my R outer is like that one, right? So the R outer is going to be 1 minus that x value, and my R inner is just going to be the x. So again, for the other piece, I have 1 plus sine pi x. So when I solve this for x, is that okay there? So my R outer was 1 minus that function. And my R inner was just that one function. And that's much, I think, tougher to get to than using a shell there. Not that it was impossible to get it without using a shell, but I think the shell was made that a much easier problem. You know, the setup was really clean and neat. You didn't have to solve anything in terms of a y or in terms of x's to get the integral in terms of y's, that's awesome. I love that. I didn't have to break the integral into two chunks, which again, like, not that bad, but like, would I rather do one integral or two? I'll take one most of the time if you give me the option there. But that's the idea. Again, you could have done it either way. Hey, how's it going? Good. Not a bad shell though, right? Elaine, does that feel okay? Again, like for the test format, you'd be given like, you know, something like this, and you can use any method to find it, whether you want. I would not tell you use a shell, use a washer, use discs or whatever, you know, like I will let you choose, but like being able to choose which one is going to work and what's going to be easiest is going to be the kind of the hard part, right? All right. So today I'm going to call like a little bit of an audible. Actually, I don't want to. And I want to talk about some extra integration techniques that we can do for dealing with rational functions. So we're going to look at several different situations. And we'll talk about the technique that we can use to deal with that. The first situation is going to be a degree greater than 2 over a degree 1. So let's say we have y equals x cubed plus 7x squared minus 3x plus 5 over x plus 4. Now, as this is currently written, we don't have an integration technique to handle this. You can't u sub it, because either you pick the top or the bottom as your u. The leftovers aren't gonna solve any of your problems here. The trick here is what we want to use is we want to do polynomial division. So remember there's two polynomial division techniques, right? There's long division and synthetic division. Long division you can always do. Synthetic division you can sometimes do. What is the condition you need to have in order to do synthetic division? The denominator has to be monic. That means that the denominator has degree 1 and leading coefficient 1, which is what we have in this example. So let's do that. So we set up our synthetic division. we roll through that. So what this allows me to do, remember that the last number is the remainder, then the constant, the x coefficient, the x squared coefficient. You just kind of keep walking your way up. So can I integrate this as it's currently written? That's a big 10-4. That I can handle. So again, if we had the integral of this guy, we can rewrite it as the integral of this Is everybody okay on how I did the division and changed it? And now this integral is not too bad, right? The integral of x squared, x cubed over 3. The integral of 3x, 3x squared over 2. The integral of negative 15, negative 15x. How am I going to do the integral of 65 over x plus 4? I'm not going to break that apart. That's a u sub. So the u is going to be the x plus 4. And then du dx is just 1. So du is just dx. So really I'm integrating 65 times the integral of 1 over u. What's the integral of 1 over u, the antiderivative? The natural log of u. Very good. So in this case, we're going to have 65 natural log of, and then instead of u, I'm going to write x plus 4. And that's supposed to have an absolute value around the natural log. And then the plus c at the end. So the synthetic division is the trick there. If you have a monic denominator, and I probably shouldn't, I should say should be greater than or equal to 1, actually. That would be okay. Is everybody cool with that? That's kind of the easiest of these techniques to deal with a rational function, is where all you have to do is that polynomial division, and then just, it's an easy u sub integral afterwards. Would we like to see another example of that, or is that okay? This feels okay? All right. So situation 2, so the next situation is we have a degree 0 over an even degree trinomial. Actually, I'm going to do that, make it a little bit trickier. So let's say we have 7 over x squared plus 4x plus 6. Now notice that this is not something we can u sub as it's currently written, because your choice for u sub would have to be the denominator, x squared plus 4x plus 6. But if I go and I take the derivative, I still have an x term left, then I can't substitute that out anywhere, so it's not gonna work for us. The trick here is that we're wanting to use the tan inverse antiderivative. We're going to use that with a u sub. So what I need to do is I need to figure out a way to rewrite this denominator as something squared plus a constant. You know what? I think I am going to make that a 5. I changed my mind. Do you remember how to do that? How do I take a trinomial, an even degree trinomial, and write it as something squared plus a constant? That's the one, yeah. Whoever mumbled it, completing the square is exactly what we're looking for. So what we need to do is we need to add the b term divided by 2 squared, and then I have to like subtract it right afterwards, right? Same as doing nothing at all. Everybody kind of remember doing this? So what I do now is I'm going to group together this piece, and this piece. And do a little simplifying. X squared plus 4x plus 4 factors to x plus 2 squared. And then 5 minus 4 is just 1. So what we can do then is we can do a u sub where the u is going to be that x plus 2. So du is just going to be dx. So when I pull the 7 out front, I can do this, which is my tan inverse antiderivative. And I'll put my u back in plus c. How's that one look for you? So again, the trick there is using the completing the square to get things to work out. If, for example, you do this completing the square and you don't have a plus 1 left over, and there's not like a coefficient here either, to where like, okay, maybe I can just factor like a half or something out of the, factor 2 out of the denominator and just make a 1/2 out front. might not be the method. This might not be the method to use then. We still have one more situation that we want to, or one more technique to talk about. And then my last situation okay, so this is going to be the most versatile, is where the degrees almost don't really matter a whole lot. So let's say we have something like this. Maybe I should include the denominator. What you're looking for is something that's factorable, though. All right. So this denominator, I notice factors. That's x plus 2 times x plus 3. Everybody cool there? So to get that fraction, I must have added something over x plus 2 with something over x plus 3, right? Everybody agree with that? So that's what I need to do, is figure out what those a and b are. Then I'll get it into a form I can integrate. This process is called a partial fraction decomposition. Do you guys do that in pre-calc still? Any kind of answer there, even if it's no, would be okay. Just allows me to, like, how careful do I need to be? How, you know. Okay, so assume that this is the first time you're seeing this. Very good. That's fine. Okay, so this is what I want to do, is I want to figure out what the a and b are to do this. This is an equation, right? So I'm going to think about this as an equation, and I need to solve for the a and the b here. So what's the first step in solving a rational equation like this? I'd want to clear the fractions. So I would multiply both sides of this equation by x plus 2 times x plus 3. When I multiply that on the left-hand side, the denominator just cancels out, and I'm left with x plus 1, right? When I multiply it to the right side, I have to multiply it to each term. When I multiply it to the first term, the x plus 2's cancel out. So I'd be left with a times x plus 3. And when I multiply it to the second term, the x plus 3's are going to cancel out, so I'm left with b times x plus 2. So far, so good. I'm now going to distribute the a and b's through. Very good so far. Now what I know here is that ax plus bx has to equal x, right? And I know there's like a coefficient of 1 in front of that x. So I know that a plus b has to equal 1. And I know when I add up that 2b and that 3a, that also has to equal the constant term. So 3a plus 2b has to equal 1. That's going to make for myself a system of two equations. I can solve that system now using any of my methods that I previously learned. What are some methods that we have to solve a system of two equations? Substitution. What else? Elimination, I think, is the one that you're talking about, canceling. But guess which one I'm not going to use either one of those two. You know what I'm going to use? I'm going to use a matrix so I can just do it on my calculator. Now, substitution, elimination, both fine. They'll both work. I'm going to just do it on my calculator, though, because, well, my time is valuable, and like sometimes substitution or elimination can be a little bit lengthy, particularly if you have like a 3-variable system or more, which no thank you. So what I'm going to do is I'm going to enter this system as a matrix. So I'll press second and the x to the negative 1 button to open up the matrices menu. I'm going to go to the edit tab. So this system I have has 2 rows and then 3 columns. So I need a 2x3 matrix. The entries in that matrix are just going to be the coefficients from the column or from the equations. So first row is 1, 1, 1 for 1a plus 1b equals 1. The second row will be 3, 2, 1 for 3a plus 2b equals 1. Once I have my system entered, I'm going to exit out of the matrix menu and then go back into it. So second x to the negative 1 again to open the matrix menu. This time I'm going to go over to the math tab and I'm going to scroll down until I find the command rref. Make sure you get the one with 2 R's. I'll select that and do that on matrix A. So what that tells me is that the value for A, 1a plus 0b equals negative 1, so A is negative 1. And then 0a plus 1b is equal to 2, so B is equal to 2. So if I then had this integral, I would rewrite this as this way. That's a bad looking 2 there. Do a better job. So far, so good. It's okay. Now, to integrate each one of these 2 rational functions, since they are degree 0 over degree 1, I can just use that u sub with a natural log, you know, where the first u is x plus 2. So again, just du is dx. And then we'll use a v for the second letter. So again, dv is just going to be dx. So when I integrate this, I'm going to have negative 1 natural log absolute value x plus 2 plus 2 natural log absolute value x plus 3 plus c. And now my assumption would be that this would not be, if this is a multiple choice question, this would not be the way that the final answer would be written. This is fine if it's a free response question. If it's a multiple choice question, what are they going to do? They're going to use their rules of logarithms to condense this into a single logarithm. So what does a coefficient out front of a logarithm mean? It's going to be an exponent inside the logarithm, right? Like that. So I could do that, right? Now, the absolute value of x plus 3 squared, do I still need the absolute value there? Why not? Because it's squared, so it's always going to be greater than 0 anyway. So that's fine. And then what does addition between two logarithms allow us to do? Multiply them. So I'm going to end up with like and that, oops, let's see, would probably be what I would expect my final answer to look like, or something very close to that, where they've done some condensing to their final answer. If it's a free response question, there's no need to do that. But if it's a multiple choice question, I would expect to see like a fully simplified answer as my choices and not something else. Let's do one of those again, right? That's the kind of the longest process and I think the trickiest of them. And I'm going to say a couple of things here before we get going. This partial fraction decomposition that we're doing, we're only going to do the easiest version of it. I want to state for the record that, like, if you have, when you do the factoring, if there's like a term that's repeated, so like if you had factored it out and you had like x plus 1 squared in there, the process has a new wrinkle to it. Or if you have factors that are quadratic or cubic, that aren't just like degree 1 factors, the process gets a little bit more complicated. There's some more wrinkles that we add to it. It's still the basic same idea, but like, it can be a little bit more complicated. And we'll do like one example where things get a little bit more complicated just to kind of show you what that would look like. So let's do that now. I'm going to just pick one where it gets more I would never ask you to do the more complicated one on a quiz or a test or whatever, but I think it's worth showing you. So let me try not to screw this up too badly. Let's try that. So there's clearly nothing like any of the other forms, right? We have degree 5 in the denominator, like that looks rough. The first thing I want to do is to fully factor the denominator. So x to the 5th plus x squared, how can I factor that? Take out an x squared. Okay. What else? X cubed plus 1 can factor more, right? That's the sum of cubes. Now, you probably don't remember the factoring pattern for that. That's the factoring pattern, though, if you didn't remember. All right. So what things would we have had to add together here to get this? Well, I could have like a over x squared, but I could also have an a over x, right? Or I'm sorry, a b over x. And then I can have like c over x plus 1. And then the x, oops, I actually screwed this up already. Hold on a second. And then I can have let me just get rid of all the letters. And then I'll have the x squared minus x plus 1. So those would be the factors that could be added together. Now, could some of the numerators be zeros? Sure, that could happen. But we don't know that from the start, so we have to assume that like there could have been an x and an x squared because it's a repeated factor. Now, if I have a degree 2 term, it could have an x in it in the numerator. So you have to account for that. Again, could there be no x in those numerators? Sure, but then just like a will end up being 0 or e would end up being 0, and that's fine. So that's my setup. That's the system I'm going to have to solve for. I have 6 variables there. You can see why I don't want to do this by hand, Michael.
How come for the first one we have the x squared instead of the x with the x?
Because again, if I have like 1 over x plus 2 over x squared, that's still going to just give me something over x squared, right? So because the x is a repeated factor, I have to include like if it's a degree 1 or a degree 2. If it was x cubed, I'd have to have an x cubed, an x squared, an x to the first. Those are all possibilities that are still stuck in there. Very easy to miss that, but there's lots of ways that I could still end up with that same denominator by adding pieces together. Does that make sense? Yeah, that's a tricky one to remember. All right. So we'll take this and then we'll multiply both sides by that x squared plus x plus, or times x plus 1 times x squared minus x plus 1. And we're just going to get just a colossal mess now out of this, aren't we? I picked a problem way too complicated. And then what was my numerator at the start? X cubed plus x plus 1. Okay. Yuckarooskies, right? This looks terrible. Couple of observations, though, that'll make this life easier. Those things, well, that just multiplies to be x cubed plus 1, right? So that's 1 FOIL is a lot easier than 3 FOILs. There's no triple in there. So I'd have ax to the 4th plus bx cubed plus ax plus b. This guy is going to just be x to the fourth plus x. So I have plus cx to the fourth plus cx. And this one's going to be dx to the fourth minus dx cubed plus dx squared. And then again, we'll just multiply those together and FOIL again. So I'm going to have ex to the fourth minus fx squared minus ex to the third minus fx squared. Oops, oh yeah, that is right. And that's going to equal x cubed plus x plus 1. So if I take my degree 4 terms, this guy, this guy, this guy, this guy, we add those together, a plus c plus d plus e has to equal 0. And then we'll take my degree 3 terms, so b minus d minus e has to equal 1. And then we'll take our x squared terms. So I'm going to have d minus 2f. That has to equal 0. And then we'll have our x terms. A plus c has to equal 1. That's not what I meant to do. That's fine. I don't care what color things are anymore. And then our constants b has to equal 1. And then it's solving the system from there, right? Now, I would never ask you to do something that has like this much in our system, because like what a nightmare this looks like. And it might even be intractable. Like there might be like infinitely many solutions to this or something. But that's the setup, what you'd have to do. Michael?
Can you go back up that question?
Yeah.
For the, how did you, like, you had C and D like by themselves, but then you had like AX plus B, like, how did you pick the letter variable for that?
So every possible coefficient gets its own separate letter. So because this is over x squared, it could be degree 1 or degree 0, the numerator, right? Because it's over a degree 2 term. This is over a degree 1 term, so it can only be degree 0, can't have an x on it, right? This guy is a degree 2, so its numerator can be degree 1 or degree 0. You know what I'm saying? So that's why I get those extras, why some of them have x's and some of them don't. It's the ones over the degree 2 terms have an x in there. Now, the thing I would give you on a test or whatever would look like the first example. Okay? But I wanted to show you like the partial fraction decomposition is like, you know, can be kind of hairy. Again, I would way beyond the scope of what I would ask you to do, but it's still the same idea. I don't think it's wrong to do a messy example and show you how messy it can get, as long as I'm clear that like I would never make it this messy for you in practice. What do you guys think? Should we do another easy one? Yes. Yeah, let's do that. All right. So we're just been circling back to these integration techniques. So why don't you guys take a minute and try to do this one here just on a separate sheet of paper. I'll give you guys 5 minutes or so to kind of pick away at this, and then I'll start adding in my own work.
Yes, little?
No, she might not be. Thank you.
I don't make mistakes.
I love that we're talking trash about our math abilities right now.
You have to use them at least once. You're gonna use them. So you're gonna have all your like 4 tribes and stuff. So these are your 4 tribes. And you're gonna want to that's religion. That's your religion, the aboriginal, and this is not something. Okay, that's fine. I'll make it up. What did you say? I think we can, and you can tell us the truth about all that. You have to get to know, you need to do the definition, but you have to know all of them, about all of them. No. Yeah. Of each. One person. I'm gonna compare and contrast.
You might as well just join trial.
This is a situation.
Yeah.
I'm explaining.
I don't see it written down.
I think you might be alone.
Yeah, you got that.
Left ear.
I like this.
Too loud.
And then this.
You don't do everything does this?
So you're done with any service hours? I went to forgot.
You went to Forgotten Harvest? No, we went.
That was quick.
Okay.
This is from a virtual that I guarantee you did on a virtual.
I'm never coughing for your Celsius. It didn't go good.
Never mind, don't.
Because I did not do well.
No, I.
I couldn't finish that. Yeah.
No, Addie.
Hey, me too.
Addie.
Oh my gosh, that's the super cool. Wait, guys, I never. I literally, I did like the first step.
Yeah, I got.
No, I'm gonna look over some stuff for that. Hey,
I guess I need to work better on that. I know that's a lot. Part two.
I don't know.
I usually get around like 70 or like 80.
That's such a
Not this time.
Oh, well, the extra
No,
cash.
no, I don't.
It's like,
Nice, so how about?
if you walk to the class, you know, you can tell.
Can we still buy this? Did you do that?
I was on track to get at least up to like an A.
real magic.
I don't know if that's
So make this.
You guys have to do the basics.
I can't wait to see as much as
Oh, no. I know.
So we use that as a guide.
That's why I was asking.
So I did it,
So when I say that,
like, I took it the week before break. And like, then nobody else did the test back.
No one did it. I don't think anyone did.
Well, that's what I'm saying, but so many people that I don't think get the test, so she wouldn't give it.
Michael, did you need to do test corrections for bio? Did you do that? So, just use it.
She told me that we have all of this.
Oh, okay, perfect. Thank you. Tomorrow. I was finished last night Thursday, and then, yeah. And Friday we were 5 o'clock.
I'm studying for that. Wait, so.
Yeah, we sure do.
Yeah, Friday, I'm not
Mr.
sure.
We sure do.
Yes.
I want to begin the looks like we went A plus B equals 2.
I don't mind
3A
those.
plus
Honestly, it's not
Mike's,
bad.
I know, it's just.
So I looked at the x's, ax plus bx has to equal 2x.
Oh, yeah, me too. Then you pulled.
So if I add those together, a plus b has to give me 2.
I got.
And I did the same thing with the coefficients then. 3a plus 7b has to equal 5.
Like I understand, but I just.
No problem.
Oh, I
My answer was natural law.
I made it.
Your answer matched.
So again, if you were doing this as a if you're doing this as a free response question, that thing in blue would be correct. There's no need to simplify past that point. But if it's a free response question, the thing in red would be the free response choice. They would expect that you fully simplified something for a multiple choice question. That's the answer they would represent. So, like, don't let that throw you. All right, here I got another one for you guys.
I got step 1 down. It's like, I'll do step 1, you do step 3, 4, 5, 6. What about step 2?
Yes. Sure. I'll give you a hint. This is not partial fraction decomposition. How can you tell?
Degree 0.
Yeah, the numerator is degree 0. What else, though? The bottom is not factorable. Okay, if the denominator is not factorable, it's not going to be a partial fraction decomposition. So it's either going to be using tan inverse or division. Can it be a division problem? No, because the degree of the numerator isn't greater than or equal to the degree of the denominator. So this has to be a tan inverse problem. So you have to use completing the square here.
Take the inverse. Take the inverse. No, you really touch me told you're using your own. You proved you proved.
I like putting those in my chest.
So that's the easy step. What am I going to have to do here, though? Because it's still not in a form where I can use that tan inverse antiderivative. What? I can't U sub it yet to cram it in to make it a tan inverse antiderivative. I mean, I can U sub, but it's not going to get me anywhere. What's the problem? Yeah. What does this need to be? Okay, so what should I do then? I have to multiply the top and bottom by like 1/4. But now what's the problem? I have that 1/4 there outside of the squared, right? What do you, nope. What do you notice about 1/4 though? No. It's 1/2 squared. Yeah, you would just end up. No, there is, because now since it's 1/2 squared, I can push it inside together. Now we're in a spot where we can U sub. This is as tricky as they could get for you guys. Woo! Now the hardest part there was recognizing all the places where it's like, nope, still can't cram this into a tan inverse U sub, and keep pushing ahead forward to getting it like crammed together to where you could do that. Again, this is probably harder than something I would ask you to do on a test because of the extra steps there. But like the AP would, I pulled this from the My AP site as one of the test bank questions. This, in my opinion, is like one of the harder ones that I've seen as a multiple choice integration problem, where it's like it's a lot of layers to this to kind of sort through. But this was on the MyAP. Just letting you know that I think this is harder than something I would ask for you to do, but somebody wrote this question for their kids that thought this was a fair question and put it up there, or the MyAP people made it and put it up there because they thought it was a fair question. So what do you guys think? So today the question was, like, how do I integrate a rational function? We saw 3 ways to do that, right? If the degree of the numerator is greater than or equal to the degree of the denominator, we're going to use division and then a u sub. If the degree of the numerator is 0 and the denominator is, like something you can do completing the square with, we're going to use this tan inverse trick. Anything else, particularly if the denominator is factorable, is going to be a partial fraction decomposition problem. What do you guys think? So those are the 3 main ways to do this. Now, there's another technique still later that's more versatile than any one of these that are kind of super specific that we will look at, but we'll do that on the next test. This felt like enough for today, though, these 3 techniques. These don't necessarily correspond nicely to to textbook pages. So I'm going to just pull, like 10 or 20 multiple choice questions kind of concerning these topics and mix them all together. And I'll put that in would you rather have me drop that into the OneNote, or you just want to do it from the MyAP site? What's easier for you guys? OneNote? Okay. Yeah, I'll make a PDF and drop it into the OneNote before we leave today. That'll be there. And it'll just be covering these 3 topics, but they won't go like necessarily all in order. Cool? And they're MCQs, so that's like eminently checkable. Try to do them without a calculator unless it has the little calculator thingy majigger by it, just for practice sake. But I will cap at 20, no more than 20, probably closer to 15. But I haven't sorted through to look for stuff yet. Okie dokies. Okay. I think that's good for today.